Okay, so welcome. Today we're going to take a look at work and its relationship to energy and motion and gravity. Let me quick level this out again. Okay, so when we're talking about work is a way of transferring energy using a force over a distance. I'm gonna write that in. And transfer of energy through a force acting over a distance. So that if we do work, we have a way to calculate this, which I'll get into in a moment. But I want to demonstrate what we mean a bit by energy in the context of physics. So when we exert a force over something, or allow something else, like say the Earth, to exert a force over something, then what we're doing, what's the difference in this? So let's say I have this ball here, and I've lifted it a certain height, and it's about maybe 1.2 meters off the floor, and I let it go from here. If I release it so that just gravity is acting on it, then it drops and it gets to the floor with a certain speed. It's changing its behavior, it's changing its motion, and it's speeding up while it does so. And there's a difference in how fast it's traveling when it gets to the floor. If I had dropped it from 1.2 meters and let gravity work over those 1.2 meters, then if I take it up to like 2 meters and drop it from here, and it's going a little faster when it gets down to the ground there. So what does that look like? What do we mean? What does that mean as far as this thing called work is concerned? So the operational definition for work, the way that we calculate or measure work, is that it's the product of the average force applied over the distance that that force acts in the same direction as that distance. Or we could write it down in an equation. W for work is net average force times the distance over which it acts. And they have to be lined up in the same direction, the force and the distance. When I'm dropping the ball, the force that's being applied to the ball is its weight, force of gravity. And it's in the same direction as that distance. It gets to do work on the ball, and the result of that was that it changed the ball's speed. Now I can take a force and exert it on the ball, and not exert it in the same direction as displacement. For instance, when I have the ball here, I'm supporting the ball with a normal force from my hand, balancing the weight, so that the net force acting on it is 0, so that there's no acceleration. And so the velocity of 0 in this case stays the same. I'm not doing any work on it now because the total force acting on it is 0, so there's no work in that respect. And the amount of work that I'm doing on it is also 0 because there's no displacement. There's no distance that's traveling in the direction of that normal force. Now, if I were to walk at a constant velocity, then while I'm walking at that constant velocity, I'm also not doing any work. Because there's, well, for one, there's no force in the direction of motion if I'm going at that constant velocity. I still have the normal force upward to balance gravity. And so that means that I am exerting some force on it, however much this ball weighs, but no part of that normal force is in the same direction as motion. Now, I did have to exert a force on it in the direction of motion to begin moving it along in that path, to accelerate it in that direction from rest. And then I had to slow it down again, exert a force in the other direction, do negative work to do that. And so those are instances of doing work on the thing. When we're changing the speed, we were accelerating it and we were doing work. Now, so I said work is a way of changing energy. So how do we relate then that energy to the motion and speed? Well, let's take a look. We're going to derive a little bit of something here for that. So, so let's see. Let's try to set this up so there's minimal glare. All right. So, we said that work is force times distance here. And we remember from earlier experience that the Newton's second law tells us that the net average force is mass times acceleration. So that then gets to tell us that the work is mass times acceleration times the distance over which we're accelerating. But we also had relationships between acceleration, average acceleration, and velocity. We have a few of those, and we derived them in our unit on motion. I'm going to put down one of them right now for saving time here. So when we had motion and the acceleration and the distance traveled were in the same direction as each other, and then the relationship between those and the speeds were as we see over here. Final velocity squared minus original velocity squared is twice that acceleration times that distance traveled. So we can go ahead and take that. Let's color code this a little bit. let me, I'll solve for acceleration times distance over there. And then we can go ahead and take that and substitute that in to our relationship for work. And what we do we get another relationship here that just relates work to mass to the original speed and the final speed. And we can, I need a little more space on this. And because we can rearrange that again so that we have two terms. We'll distribute that m divided by 2. And we get that the work is the difference between some combination of stuff for its final condition and the same combination of stuff for its original condition. And so this is some quantity. This is some quantity that is changing with time. That work is changing. And we can give the thing a name. And we'll call it energy of motion. And in Greek, our Greek root word for motion is kine, K-I-N-E. So kinetic energy is energy of motion. And it's that which we are going to define as being 1/2 mass times speed squared. And so if that's the case, then we get back to the idea we had earlier, that when that work is equal to a change in energy. And in this case, if the work is going all into changing a thing's speed, it's changing the kinetic energy of the thing. Another thing that we didn't mention here, work of course has to have units. And it's the same units that we have for energy. Same units for work, same units for kinetic energy, same units for energy you've encountered in other situations in other classes like chemistry, biology, or any of your other sciences. And what are those units? Well, the units of work, since work is net average force times distance over which the force acts, that's the units of force times the units of distance, or newtons times meters. And we could go ahead and call them that, but we decided we're going to go ahead and give that unit its own name. So that unit we call a joule. but it's after a person's last name, so it's not spelled like something that includes gems and precious metals and whatnot, but it's named after a fellow by the name of James Prescott Joule, who did a lot of scientific research about the transfer and transformation of energy in the mid-1800s. So it's spelled Joule, and if you're writing out the long way, use a lowercase j, but if you're using the abbreviation, it's capital J. And it's the same thing as a Newton meter, which is the same thing as a kilogram times a meter squared per second squared. All of this is also, these end results are all in the notes that I distributed earlier for those of you in the CP1 physics class that is associated with this video. And so let me pause for a sec here and go on for another couple of ideas here. So we have our work is net average force times the distance in the same direction as that force. It can change energy, change kinetic energy, and we've got a definition for kinetic energy. It's related to speed, square of the speed. The next thing we've got is that, well, we've seen this before where we're multiplying one thing by another thing, and we're dealing with averages, and it's the force averaged over the distance. It's the first thing averaged over the way the second thing changes. Like when we're multiplying acceleration times time, or change in time, and that gave us the change in velocity, or the average velocity times change in time, gave us the displacement. And when we were multiplying those two terms together, those were always related to areas in graphs. So this is also equal to the area under a force, net force, versus distance graph there. And if you have the force changing in more complicated ways, you have to use more complicated math to figure that out. That's integral calculus, which we're not using in the CP1 class that this video goes with. We also know that if we've got relationships with the product of two terms, and that's an area, we can change these around a little bit, get another equation, and we can get a relationship with fractions. Although I'm not going to do it with this equation directly for now. Instead, I want to look at another rate. The rate at which we do the work, the rate at which we change the energy. And that is what we mean by power. Same power you run into in your electric bills. Same power you talk about with how much output a car's engine may have. It's the rate at which energy changes with time. And whenever we're dealing with rates, we're looking at like fractions and slopes. So power is change in energy, or in this case, work, divided by the time for the average power. And it was changing in a more complicated way, and we want to know the exact power, then it's the slope of a work versus time graph. That P is supposed to be the same type of P. Now we used lowercase p to represent momentum. This is supposed to be a capital P for power, and I'll emphasize that by sticking some serifs on it. And it has units of units of work divided by units of time, which are joules per second. But it's also the same unit that you run into in everyday life when dealing with electricity. And that's the watt, named after James Watt, the fellow who invented the condensing steam engine, and the fellow who derived another unit for power, the horsepower, which was a kind of a funky thing. He claims that the horsepower was the energy, or the rate of energy, the rate of power, rate of work done rather, by the average English draft horse to lift 550 pounds of force 1 foot in 1 second. The average English draft horse was capable of doing that power. So 1 horsepower winds up being 550 foot-pounds per second, and that's about 746 watts. So a watt is a little smaller than a horsepower. Okay. Let's see. Let's stop for there. And we'll discuss some other things in the next video.